Hello everyone. Today we are going to analyze this beam using moment distribution method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 50 kN acting at 2 meter from the point A. In the span BC, there is uniformly distributed load 24 kN per meter acting for the full span. In the point A and in the point C, we are having fixed supports. In the point B, there is a hinged support. Span AB is 5 meter long. Span BC is also 5 meter long. In this beam, we have to calculate 4 moments. In the fixed support, there will be a moment. In the point A, we are having fixed support. So, there is a moment MAB. In the point C also, we are having fixed support. So, there will be a moment that is MCB. In the joints, there will be two moments. We are having only one joint, that is joint B. In the joint B, there are two moments, MBA and MBC. Also, we have to calculate three reactions, RA, RB, and RC. Now, let us calculate the fixed end moments. For calculating the fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Before calculating the fixed end moments, let us see the formulas. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, there is a point load which is not acting on the center. So, we have to select this condition. The fixed end moment formulas are minus WAB square upon L square and positive WA square B upon L square. In the span BC, we are having UDL for the full span. So, we have to select this condition. The fixed end moment formulas are minus WL square upon 12 and positive WL square upon 12. Now, let us apply the formulas and find out the fixed end moments. In the span AB, we are having a point load. This point load is not acting on the center. In this case, we have to split the span into two parts, A and B. We have already seen the fixed end moment formulas minus WAB square upon L square and positive WA square B upon L square. M of AB will be negative because it is acting in the anti-clockwise direction. M of BA will be positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 50, A is 2 and B is 3. After calculations, we are getting M of AB is equal to minus 36 kN meter and M of BA is equal to 24 kN meter. Now let us calculate the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We have already seen the fixed end moment formulas minus WL square upon 12 and positive WL square upon 12. Let us apply the values inside the formulas. W is 24, L is 5. After calculations, we are getting M of BC is equal to minus 50 kN meter and M of CB is equal to 50 kN meter. In the moment distribution method, we have to calculate the distribution factor. For calculating the distribution factor, we have to find the stiffness. in the point A and in the point C, we are having fixed supports. In the fixed supports, the distribution factor will be 0, so there is no need to calculate the stiffness. In this case, we have to calculate the stiffness only in the joint B. Let us see how to calculate the stiffness at the joints. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. Now let us use the formulas and calculate the stiffness. From the joint B, we have to calculate two stiffness values for BA and for BC. To calculate the stiffness for BA, from the joint B, we have to look at the point A. In the point A, we are having fixed support. If the fair end is fixed, the formula is 4EI upon L. Here the length is 5 meter. Let us apply that. Finally, we are getting 0.8 EI. To calculate the stiffness for BC, from the joint B, we have to look at the point C. In the point C also, we are having a fixed support. If the fair end is fixed, the formula is 4EI upon L. The length of BC is 5 meter. Let us apply that. Here also, we are getting 0.8 EI. Now, let us calculate sigma K, that is the summation of stiffness. We are having two stiffness values. Let us add both of them. After adding, we are getting 1.6 EI. Now, let us calculate the distribution factor. The formula for distribution factor is K upon summation of K. For BA, K is 0.8 EI. Sigma K is 1.6 EI. When we apply in the formula, we are getting 0.5. For BC, K is 0.8 EI. Sigma K is 1.6 EI. When we apply inside the formula, we are getting 0.5. In a joint, when we add the distribution factor values, it should be 1. In the joint B, there are two distribution factor values, 0.5 and 0.5. When we add both of them, it is 1. Now, let us start making the table. First, let us enter the members. We already know in the fixed supports, the distribution factor is 0. That is why for AB and CB, it is 0. In the joint B, we have calculated two distribution factor values. For BA, it is 0.5 and for BC, it is 0.5. We have already calculated the fixed end moments. Let us enter them. Now, let us make the first distribution. The distribution can be done only on the joints. In this problem, there is only one joint, that is joint B. Under the joint B, we are having two members BA and BC. For them, we are having fixed end moments. For making the distribution, we have to add these two moments and then multiply with the distribution factors. First, let us do the distribution for BA. For that, we have to add these two fixed end moments, then multiply with the distribution factor for BA, that is 0.5. When we do that, we are getting a negative value. Here, we have to be very careful. If we get a negative value, we have to enter as positive, and if we get a positive value, we have to enter inside the table as negative. Right now we are getting negative value, so we are entering inside the table as positive. Now let us do the distribution for BC. For that, we have to add these two values and then multiply with the distribution factor at BC. When we do that, we are getting negative value, so we are entering inside the table as positive. Here both of the values are same because we are having same distribution factor value. We cannot make a distribution for AB and CB because their distribution factor value is 0. Now let us make the carryover. The carryover should be done inside every span. First, let us see the span AB. In the span AB, we are having two movements, MAB and MBA. From MAB, half of the movement will go to MBA, and from MBA, half of the movement will go to MAB. For AB, there is no distribution, so we can't make the carryover. From BA, half of 13 will go to AB, so 13 upon 2, we will get 6.5. Now let us consider the span BC. In the span BC, there are two movements, MBC and MCB. From MCB, half of the movement will go to MBC, and from MBC, half of the movement will go to MCB. So from BC, half of 13 will go to CB. 13 upon 2 is equal to 6.5. For CB, there is no distribution, so we can't make the carryover. In this problem, we cannot proceed further. In the joint B, we cannot make the distribution because there are no carryover. For AB and CB, we cannot make the distribution because their distribution factor is 0. In this case, let us stop the problem and add the values and find the final moments. We have to add the values from the fixed end moments. When we add minus 36 and 6.5, we are getting minus 29.5. When we add 24 and 13, we are getting 37. When we add minus 50 and 13, we are getting minus 37. When we add 50 and 6.5, we are getting 56.5. So in this analysis, we have calculated all of the moments. For MAB, we got a negative value because MAB is acting in the anticlockwise direction. For MBA, we got a positive value because MBA is acting in the clockwise direction. For MBC, we got a negative value. That means it is acting in the anticlockwise direction. Finally, for MCB, we got a positive value. That means it is acting in the clockwise direction. Now, let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, there are two movements, MAB, which is acting in the anticlockwise direction, and MBA, which is acting in the clockwise direction. In the span AB, first I am going to find RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 5. So 5 RA. The point load 50 kN is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 3 meter. So minus 50 into 3. Then there are two moments. The moment 29.5 is acting in the anticlockwise direction, so it will be negative. The moment 37 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RA is equal to 28.5 kN. To calculate RB1, let us apply the rule summation of vertical forces is equal to 0. In this span, there are three vertical forces RA, RB1 and the point load 50 kN. The reactions RA and RB1 are acting upwards, so both of them will be positive. 50 kN is acting downwards, so it will be negative. We have already calculated RA 28.5, so instead of RA let us apply 28.5. In this way, we can calculate RB1, which is equal to 21.5 kN. Now, let us take the span BC and calculate the reactions. In the span BC, there are two movements, MBC, which is acting in the anticlockwise direction, and MCB, which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. The vertical reaction RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5. So 5 RB2. The UDL 24 kN per meter is acting towards the point C in the anticlockwise direction, so it will be negative. When the UDL comes, we have to multiply with the distance and a distance upon 2. Here the distance is 5 meter, so 5 into 5 upon 2. Then there are two movements. The moment 37 is acting in the anticlockwise direction, so it will be negative, and the moment 56.5 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RB2 is equal to 56.1 kN. Now let us apply the rule summation of vertical forces is equal to 0. In this span, there are three forces, RB2, RC, and the UDL 24 kN per meter. RB2 and RC are acting in the upward direction, so both of them will be positive. The UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance to get the total load. We have already calculated RB2. Let us apply the value. In this way, we are getting RC is equal to 63.9 kN. We have calculated the reaction in the point B 2 times. Let us add both of the values RB1 and RB2. After adding, we are getting RB, which is equal to 77.6 kN. Now we are going to draw the shear force diagram. Before drawing, let us find the shear force values. I am going to calculate the shear force values from the point A and towards the point C. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the calculations here. Using the values, we can draw the shear force diagram. Now, we are going to draw the bending moment diagram. Before drawing the bending moment diagram, we have to make the free moment diagram and then the end moment diagram. Finally, we have to combine the free moment diagram and the end moment diagram to get the bending moment diagram. To draw the free moment diagram, we have to consider every span as a separate simply supported beam. First, let's see the span AB. In the span AB, there is a point load 50 kN. This point load is not acting on the center. If the point load is not acting on the center, the formula for the maximum bending moment in a simply supported beam is WAB upon L. Here W is 50, A is 2, B is 3 and L is 5. After applying the values inside the formula, we are getting 60 kN meter. If UDL is acting for the full span in a simply supported beam, the formula for the maximum bending moment in the center is WL square upon 8. Here W is 24, L is 5. Finally, we are getting 75 kN meter. We know that when the point load comes, the diagram will be in a triangular shape. When the UDL is acting, the diagram will be in a parabolic shape. Now let us see how to draw the end moment diagram. Using the end moments, we have to draw the end moment diagram. First, we have to draw this line. We have to draw these clockwise and anti-clockwise curves according to the movements. Then we have to see the direction of the arrows. All of the arrows indicate upwards. So all of the points come above the line. Even though in the joint B we are having two movements, we have to make only one point because both of these arrows are indicating upwards. That means we will have only one point. End moment diagram will be negative if it comes above this line. It will be positive if it comes below this line. Right now all of the points are coming above the line, so it is negative. Now let us combine the free movement diagram and end moment diagram. You can see that I have combined both of the diagrams. Wherever they are acting alone without mingling with one another, we have to mark the values with the sign. Here the end moment diagram is coming alone. Here the free movement diagram, then end moment diagram, then free movement diagram, finally the end moment diagram. Wherever they are together, we are not marking anything. We just keep the space empty. Now we are going to end this session. Thank you for watching this video.